This is Physics 2, Lab 5. Introduction and Physics Concepts. The purpose of this lab is to collect data of a magnet falling through an aluminum foil tube and model the interactions computationally and compare the computational predictions and observed data. The results have the experimental average fall time of being 1.7 seconds and the computational calculated fall time of 1.49 seconds. The two important physics concepts in this lab are Faraday's law, which indicates quantitative relationship between the rate of change of the magnetic field and the magnitude of the non-Coulomb electric field, and then Lenz's rule, which is non-Coulomb electric field that would drive current in a direction to make a magnetic field that attempts to make the flux constant. In this experiment, we had a tube with length 30 centimeters, foil width of 9 centimeters, the inner radius was 14 centimeters, the bar magnet mass was 23 grams, the magnitude of magnetic dipole moment was 1.37, the free fall time was 2.75 seconds, and with the 5 trials and the 5 separate times, we came out to an average of 1.7 seconds. With the computational model, which is going to be the code shown next, we see that this is the tube, and then it creates this velocity versus time graph where it gives us a calculation of the average time in tube in seconds being 1.49, so pretty similar to the 1.7 from the experiment. But in the first part of the code, we have where we calculate the magnetic field, and now we have the calculating of the magnetic flux. Next, we can calculate the forces, gravity and net, then we calculate current, and then we calculate the typical B field at each ring, and finally we calculate position and velocity, and this is using the initial values that were given with the mass of the bar magnet. Interpreting the simulation, first part, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring, which color corresponds of red and blue to clockwise current or counterclockwise. How can we know? Blue is counterclockwise, red is clockwise, and this is since there's a downward increasing change in flux, meaning that the induced current is flowing counterclockwise. As we can see on the tube model, it had blue on it. What happens to the dynamics of the system when you flip the magnet around? If the magnet were flipped, the current would flow in the opposite direction, but the forces acting on the magnet and the total time in the tube would still be the same. How does the total time in tube of the real-world system compare to the computational system, and how might the computational system be more accurate? The total time in the tube of the real-world system is longer than the calculated computational system. The computational system could be made more accurate if it took error resistance into account. What does the shape of the velocity versus time plot tell us about the forces acting on the bar magnet? The velocity instantly decreases and then plateaus for a long period of time and then decreases again. The plateau indicates that the bar magnet is not accelerating, so for this period of time while it's in the tube, the gravitational and magnetic forces are balanced. The additional questions are, what if the resistivity of the conductor was reduced as close as possible to zero, and how would the dynamics of the falling magnet change? If the resistivity of the conductor approached zero, the induced current would increase, thereby increasing the magnetic force, and therefore the magnet would fall slower. What if holes or slots were cut into the tube, and how would this affect the ring currents in the model? If holes or slots were cut into the tube, the resistance would increase because there are fewer complete rings, so it would then decrease the induced current and magnetic force, and overall this would cause the magnet to fall faster. That's all. Thanks.